So please, go ahead.
Thank you for the introduction. Thank you to the organizers again for the invitation and the opportunity to speak. Let me just quickly check. So you can hear me and you can see?
Yes, perfect.
Excellent, thank you. So I was asked to give a theoretical perspective on two-photon physics, which is a big charge for sort of a 30-minute talk. So I will give a slice of new interesting theory results for two-photon physics as follows. So, in general, what I'll talk about is, the hadronic light-by-light scattering. We already saw in Achim's talk the application of this to the G-2, but also we saw that the general study here and maybe the study of projections to particular intermediate states can be useful in the general context of G-2 discussions. So I'll try to say something about those as well. But mostly I'll really talk about these hadronic blob of the two-photon scattering in the role it plays for the muon G-2. Now, again, Achim sort of started with the Glasgow consensus and then gave you a quick view of what happened after this. While of course there has been a lot of theoretical progress, there's two things that I would like to highlight here, which have entered the white paper prediction, the G-2 theory initiative white paper prediction in some sort of direct way. And these are sort of two ways to deal with this, in a sense, from first principles. So the one is that one would do the same thing or something similar that one does for the hadronic vacuum polarization. So for the hadronic vacuum polarization, this photon here and this, okay, so there's sort of a photon here and there's this photon isn't there, this photon isn't there. So there's just a single momentum that goes through the hadronic blob. Now, since there's just a single momentum, the form factor decomposition is rather straightforward. And there is also not that much to constrain experimentally. If you were to try to do a dispersive analysis of this, you again look at projections to fixed intermediate states, but you can that this is much more complicated. Even sort of getting the organization of this right is a challenge. Once you have the organization of this right, you need to worry about how you actually get the form factors for these individual vertices. And here, experiments play a huge role. On the right hand side, there is a sketch that tells you how you could do such a thing in a first principles lattice Qcd calculation. In a lattice Qcd calculation, we formulate everything in terms of the fundamental degrees of freedom as far as we know them. Those would be the quarks, the gluons, and the photon fields. The gluons, however, in lattice Qcd are not dealt with in a perturbative expansion of quark-gluon and gluon-gluon vertices, but you have a path, you perform the path integral over all the gluon gauge configurations in a statistical manner, so that you eventually evaluate a Euclidean version of your theory directly. Because of this, when we draw these diagrams in lattice Qcd, what you see are the muon lines, the photons, and the quark loops explicitly done, because those weak contractions are actually performed explicitly. But the integrals over the gauge fields, they are performed statistically. So that's why you don't see sort of the gluons drawn here. That also explains why some diagrams here, like this one, sort of these tadpole diagrams, actually do contribute. I mean, because you have gluons exchanged, for example, between this quark loop and this quark loop. So I'll talk mostly, I have to say, about the direct lattice Qcd calculations and all the progress there, since this is also my personal field of research. Nevertheless, let me start with giving you a quick overview of progress for dispersive analysis. I say here recent results, but you can already see that this is now sort of a 5-year perspective. Now, on the timescale of these 5 years, you saw that this was sort of the similar timescale in the theory initiative, but also serious attempts have been done to do this form factor decomposition. And you get much more than one form factor and much more to constrain, but you still have some organizational principle of what dominates. So the pion box and the pion pole contributions are quite large. We already learned from Achim this morning about the need to have double virtual and maybe single virtual form factors here, and how the lattice can also help there. We have then comparisons between these lattice calculations and experimental results, where they sort of in a momentum region where both of them have access, and then you can use the lattice to go also in the double virtual region, for example. A little bit more recently, there's been some progress also for kaon box contributions, but you already see that there's a significant hierarchy between the pion box and the kaons. The eta and eta prime are significantly more important, also the actual vectors. And then, as I said before, short distance, getting the short distance constraints right, and actually sort of making the transition again from your mesonic states to a picture where quark degrees of freedom again become important, is still something that you need to think about. And often it's sort of summarized in, for example, in the white paper as these short distance constraints, but there are also ideas that enter these estimates, like summing up Reggie trajectories of many rows, and there are some models where you can do this, and then you can show that they would actually satisfy also the perturbative short distance constraints. At any rate, this is something to do, something to worry about in this approach, and something that where continued research is going on. Experimentally, for example, the actual vector resonances here, one could imagine in the 1 to 2 GeV region, some improvements would be helpful. And there actually will be an update of the theory initiative that a lot of you who are interested, I'm sure, have received a draft of, which as part of the SNOMED process in the US, which gives a quick overview of the current status of this and a longer list of the references. So I would refer you to this, and I left sort of the longer list of the references out of this slide. This is the summary then of the Seattle consensus, which is what I label here the number of the theory initiative that supersedes the Glasgow consensus. And in there, the results shown on the previous slide for the pion box, pion pole, and so forth were used. In addition, in the end, also Lattice QCD results were used and averaged, and actually had the effect of a slight reduction of all uncertainties. So the actual result in the G-2 theory initiative is based on the this progress in the dispersive methods, but also in progress in Lattice QCD methods. So I'd like to talk a little bit about what has happened in Lattice QCD, because there, since from 2015, where basically the situation was that this was not calculable in Lattice QCD, has progressed significantly to the degree that now it's sort of close in precision in the Lattice QCD calculation to these dispersive methods, and there's already 2 independent calculations now. And so I'd like to spend most of my talk now walk you through this progress. So the quark level topologies that I already explained previously are complete, in the sense that here we don't have the issue that there's sort of an infinite tower of topologies that we would need to add up. These 7s are all they are, and they still have a hierarchy among them, which is evident, of course, by the states that propagate with them, but also already when you just think about the QED charges of how the photons sort of couple to the quark loops. And in general, if you look at this, you find that the top line here, which are sort of partially connected diagrams, quark connected diagrams, they should dominate. You also find that this diagram here, which is in a sense more disconnected than this, is on the same size than this one, actually. And actually one expects that this should about cancel 50% of this contribution. So clearly, both of them would need to be calculated at the same time. Now, the more tadpole type diagrams you have, the more you have sort of the SU3 type suppression, and the further suppressed these diagrams are. The top two don't have this kind of suppression. Currently, the Lattice QCD calculations, there's, of course, more results for the top line, but also estimates for the subleading corrections are now available. So quick history of the lattice as promised. So in 2015, there was sort of the first method proposed where the QED was treated also non-perturbatively and in momentum space. Okay, so you think of this diagram, a diagram like this, where the photon propagator would be generated similarly like all the gluon propagators are generated in a stochastic way. This was sort of a first attempt. This was back then by Tom Blum and Taku Itsubushi and Hayakawa. And this demonstrated that this is possible in principle, but it had large statistical errors. And it had large statistical errors already for quite heavy pion masses. So there was a lot of work to be done. There were a few breakthroughs then over the years. So the first one was when one started to treat QED perturbatively and in position space. What that allowed to do, and I will show at the next slide sort of the details of how this works, is that the statistical noise can be reduced dramatically in the sense that things that with this method here on the top would have taken a year can be done with the same precision in about a day. So this was sort of a huge change in methodology that really enabled these modern type of lattice QCD calculations. Then you can still do it in different ways. You have to ask yourself, what do you do with the photons? You can put the photons also in a finite volume, or you can try to integrate the part of the diagram here that is not directly connected to a quark in infinite volume with a different finite volume regulator. And you then sort of create a weighting function that has to be multiplied with this quark 4-point function. And that's possible too. And they have different advantages and disadvantages. If you keep the photons in finite volume, you have a natural infrared regulator for the quark loops that keeps the size of them a little bit smaller, which helps with the statistical noise, but it comes at the cost of power law-like finite volume errors. If you, conversely, if you do this immediately in infinite volume, you only have exponential finite volume errors, but the statistical noise, in particular, if you go to physical pion mass, is quite a bit larger. So here, first papers were performed, this method was established, the method was performed. And then, with the infinite volume photons, the method was introduced. This method, the sort of the finite volume method, was introduced by RBC UK QCD, so my collaboration. The infinite volume method was first introduced by the Mainz collaboration, and then there was sort of a back and forth between the different groups, further developing these methods. So let me quickly highlight this one idea because I think it's actually rather straightforward and gives you a taste of what can actually happen in Lattice QCD. So there's actually some ideas that change more than just waiting for bigger computers. So the idea here was to not generate these photons in a stochastical way, but to pick these 2 points randomly, but with a smart probability distribution between them. Okay, so you start picking, let's say, the X, and then you know that if the Y point was far away from the X, since you have these quark propagating through non-trivial QCD background, you would have them exponentially falling off. So you know that if the Y is too far away from the X, you essentially only get noise, you don't get a contribution anymore. So clearly what you should do is some sort of importance sampling where you sample the shorter distances more than you sample the longer distances. And this is essentially the basis of this idea. The details here, how we perform this, are maybe less important, but here you can clearly see the black arrow bars are the ones of the previous method, the 2015 method, and the new arrow bars here with this new method, are more than a factor of 10 reduced in the error, in the statistical error. And since that goes with square root of n, the cost actually scales by a factor of 100, which was sort of this year-to-day improvement. Now, then further on, with this method, RBC UK QCD then in 2016 calculated for physical pion mass, the leading connected and disconnected diagrams, the first line there in finite volume and at a single lattice spacing. And you see that this is actually a bit smaller than what the Glasgow consensus, for example, was. But this was just at a single volume and at a single lattice spacing, and it was with the QED-L method, so one would expect rather large finite volume errors. A little bit later, there was a first principles calculation by the Mainz group of a forward scattering amplitude here of gamma star, gamma star. The pion pole contribution around 2019, very important result by the Mainz collaboration. And here these are sort of the details of this first calculation here. And indeed, as one expects, what was found with a single calculation here was that you get about a 50% cancellation between this diagram and this diagram. Okay, so this enhances the statistical noise again because of this cancellation. And it already, sort of first studies already illustrated that one should really worry about potentially large systematic to defined volume effects in QED. So at that point, this was sort of then the focus after 2016 of the RBC UK QCD collaboration. So in 2020 now, so not too long ago, we finally completed our work. This was just in time for the white paper. And this result in here actually was then averaged with a dispersive results. And of course, informed by other theory, including things like Dyson-Schwinger, that we also quickly, were reminded of this morning. So in this work here, we performed the continuum extrapolation, the infinite volume extrapolation. Everything was done at physical pion mass. And this is the result that was obtained by this. I'm going to give a few more details later. At the same time, Mainz also made a lot of progress. So in 2020, the first result was here at the SU3 symmetric point where the pions were not yet physical. And at 420 MeV, the pions had the same mass as the kaon. But the infinite volume and A to 0 result was extrapolation was performed. And then later, in 1 year later, so 2021, this was after the white paper, but before the Fermilab experiment, this also was then additional data was included up to lowering the pion mass. It still did not really include physical pion mass results, but the remnant effects from 200 MeV to 140 MeV were estimated. And so this was then the second completely independent Lattice Qcd results from first principles where all the systematic effects are addressed. I'll talk a little bit more about these results and sort of the current status and how to move forward in a few following slides. But at this point, I also would like to highlight that there are additional results that sort of just recently showed up at the last Lattice conference. In particular, also here related to the eta and eta prime, which for which similar to the gamma pi to gamma gamma star and pi to gamma star, the lattice can provide useful results to constrain these form factors in the dispersive method. So let me quickly talk about this result, and then I'll also talk about the Mainz result. So this is the result with it in the infinite volume limit and the continuum limit from first principles here. What you see here is a set of ensembles. This previous result that you saw, where you saw this large cancellation, was only this one ensemble here, lattice cutoff of 1.7 GeV, physical pion masses. So this is sort of the distinction between the RBC UK QCD program and the Mainz program. Here from the beginning, everything was done at physical pion mass, but of course then that also leads to larger statistical errors. In the Mainz result, there's sort of this extrapolation from heavier pion masses down, and you saw the benefits of this with a smaller statistical error here. And all right, and so the 48 to 64 cube, this is sort of supposed to control the discretization errors, so this changes the lattice cutoff. And then you have three ensembles with different volumes, where the largest one has a lattice size of almost 10 femtometer to really control the long distance physics. And one can actually find that sort of this pion pole contribution has still changes quite a bit up to these very large volumes. So this is actually quite crucial for a proper control of these errors. In particular, if you do it with this parallel like QED-L method, but also if you do it with the QED infinity method. And we also had another lattice spacing here, just to add to this continuum trajectory. For those of you who have thought a little bit more about the lattice, this is sort of a supporting ensemble that allows one to double check the size of the discretization errors here. In principle, you could imagine that you can look at differences of different volumes between this and this and this and this, and discretization errors should largely cancel, but you want to have a better understanding of that, and that was the role of this particular ensemble. Now, what one does first here is to actually establish the method. One replaces the quark loop here with a lepton loop, because then the result is analytically known. But you can sort of do the rest of the lattice calculation in exactly the same way. And if you do this, you do it at different volumes, you can check the methodology, because the only thing that would then change in the end is replacing the quark propagators in the free field with an interacting theory. And if you do this, this was sort of the first step, you can see that you extrapolate indeed to the analytic result. Then here, all these ensembles are sort of shown at the same time. You see the Pauli-like extrapolation and these finite volume effects to the infinite volume limit. And you indeed see, if you were to look at these 48i, 64i results right here, which is sort of these points right here, these were the previous results for this particular diagram, for the connected diagram. And you see that while this was, okay, so this is the infinite volume continuum extrapolation already. If you just looked at the 48 one, this was the previous result of the 10 point something. And you can see that this actually, almost doubles in size in the infinite volume extrapolation, as you can see here. If you look at the other important diagram, these disconnected diagram, you see that this also receives finite volume corrections of sort of almost 100%, but they go in the other way, so they cancel again. So you have to invest a significant amount of resources here, so that even after the cancellation, you still have acceptable statistical uncertainties. Nevertheless, you can tune the entire calculation in a way that you're dominated by statistical uncertainties, which then makes it easier to actually interpret the fluctuations in a proper manner. So if you added the connected plus the disconnected and you did it the infinite volume extrapolation, you see sort of this grow from the 5 point something that one had to the 7 point something here. The mean central value at heavier pion mass was at 10. So at this point, this is all consistent. And it's also clear what the RBC-UK-QCD collaboration here has to do. One needs to improve the statistical error of this by maybe, sort of reduce the statistical error by a factor of 2 to 4 over the next years. And this is something that is ongoing right now. Now, I also said that the subleading diagrams, there's some progress there. And, they get smaller the more of these tadpole type loops you have. So I'm just showing this. And you can see that while the other results are on the order of 10 times 10 to the minus 10, they are sort of, you can sort of cut them in distance between them. You cannot really even resolve the signal from them. So what you will do in the end is you bound the size of them with a conservative cut here between the distance of where you move them apart from each other. And that is exactly what has happened in these results right now. I apologize for having a busy plot here. I, for time reasons, cannot go into all the details of the systematic error estimates, but I am showing you the complete list here nevertheless, so that you see the what has been addressed. So quickly saying finite volume effects and modifying the fit ansatz, the continuum extrapolation, possible cross terms between finite volume and infinite volume effects that in principle should not be there, but once you use an infinite volume regulator like QEDL, you can actually mix ultraviolet and infrared scales. So you want to be sure that this doesn't introduce a larger systematic uncertainty, which this one here checks. And in overall, combining all these statistical and systematic uncertainties, you arrive at this result, which then, as I said before, was combined in the Theory Initiative white paper with the data-driven results. For the Mainz result, I have this one slide here where I break out here the separate diagrams, and similar to what I've shown before, these subleading diagrams, you don't really see a signal for them, but you can bound them. And indeed, you bound them sort of at a significant smaller size than even sort of the uncertainties of the leading corrections. But the interesting thing, again, is that you have these 7 in principle separate topologies. And once you calculate all of them, you're done. There's not this infinite tower of states that you need to sum up, because you've formulated everything already in the fundamental degrees of freedom. Good. Then finally, maybe one thing that as far as I know, the Mainz group is now focusing on is, in here you see that there's still a bit of an extrapolation to the physical pion mass. And these things are, particularly because they're sort of dominated by pion poles, are quite sensitive to the pion mass. So this would clearly consolidate these results a little bit if one were to also include these simulations at lighter pion mass. And that is also ongoing.
Christoph, you still have 5 minutes.
I still have 5 minutes. Thank you very much. So I'll leave time for discussions. But thank you, because I'm essentially sort of at the end of my presentation, putting everything together, including the Mainz result here, which was just put online after the white paper was published. You see here that for the light by light, the situation is actually, uncontroversial. You have, even if you put the Glasgow consensus here too, you would see that this is, apologies, so the Glasgow consensus is here. You see that everything is consistent. I think it was very important that the theory community put in this effort, because I certainly remember the situation before these light by light calculations were started, that a lot of people were worrying about sort of the light by light, and maybe the light by light was sort of an important ingredient in understanding what's going on with attention. And this hypothesis does not seem to hold. So the light by lights, whether you do it with Lattice Qcd in first principles, whether you do it like RBC QCD does, first focusing on physical pion mass, or whether you extrapolate from heavier pion mass down, there is really no sign of tension so far. And also I should say that for the white paper, Mainz and RBC QCD, through the platform of the theory initiative, did a lot of additional cross checks, at heavier pion mass, at the time when the Mainz paper did not yet publish their results. So this is, I would say, rather well established. And right now one can at least say that the light by light does not seem to play a major role in understanding the tension. This in particular important aspect of this is also important for the discussion which we're going to have this afternoon, is that in this calculation we sort of also have separate lattice calculations at similar precision for this particular quantity. And certainly what you want to have is this independent set of systematic choices, and then demonstrate consistency again, just to make sure that, or to get a better feeling of how some choices for error estimates play out, against actual comparisons with different reasonable choices of error estimates. So the light by light is also in a situation where you have, in the same method, separate results. And maybe we can discuss this then this afternoon for the lattice HVP, where maybe, or the hadronic vacuum polarization, where maybe right now sort of more interesting things are going on. This is still work to be done if you look at the entire hadronic vacuum polarization. But if you were to look at some sub-contributions where many results are actually available at high precision, you would find already sort of interesting tensions, which we could talk more about this afternoon. Okay, that's what I have. Okay, sure. I mean, this is just details of the lattice calculation, sorry. There's ongoing work, and over the next few years, the lattice errors will come down further. Thank you.
Thank you very much for this nice, but also very detailed overview talk. Other questions, comments? Achim, please.
Yeah, I mean, it will come down further, was your statement. Of course, the question is, what is your estimate, how much one can further improve based on the lattice?
Yeah, so this is the beauty of the lattice, that in principle, the answer will be, well, it depends how long you wait, it depends how many resources one has. There is not a stumbling block that I can identify that would provide a hard wall for the precision. You can, as always in these calculations, you can make different choices, in particular whether you shift systematic errors for statistical errors. And so therefore, this is actually something very important to consider. For us here, this calculation is completely dominated by statistical errors. So I can tell you that what we need is square root n. We need more statistics here. So it's actually rather straightforward to tell you how this will progress. And for this, we have sort of ongoing work. The statistics is more than doubled right now. So the next update of this particular method should sort of have a 40% reduced error bar. But then you can again go ahead and shift some of the statistics for systematic errors in different ways. And then it's a little bit more difficult to predict. And then you just need to control these different systematics in separate, in sort of believable ways. For that, therefore, my answer is more speculative. But I would say that the RBC result here can certainly go to sub 10%. And the MINDS result, I think there, the charge is really more consolidating this and making sure that the pion mass extrapolation from 200 MeV down to physical pion, that, this is solid. So I would guess that when MINDS has an update of this with physical pion mass, that their error at first doesn't change, but that it sort of becomes a little bit even more robust by not having to do this extrapolation. While here, clearly the statistics will change a lot, and they should sort of, the next iteration should sort of have 10% like uncertainties.
Mm-hmm. Okay, thank you.
But then the question is always, and sorry for answering more than I need, we all have 24 hours in the day. And right now, I think a lot of people will focus more on the HVP, because this seems like it's uncontroversial. It seems like this is sort of approaching some stable level. So I think that the light by light, probably most of the progress will be finishing up this at sort of the 10% level, maybe waiting for new lattice collaborations to join. But all these lattice collaborations that you see here also have programs for the HVP, and they will likely invest more effort in the HVP high precision calculations over the next few years.
Yeah,
I mean, better here too.
Yeah. Yeah, I mean, that is probably for the discussion, but yeah. I made this statement already that older estimates of HVP, especially by the KNT group, they had actually an uncertainty for HVP, which was smaller than the light by light. And now, of course, within the white paper, one has this more conservative approach where one actually has tensions between different data sets, but also tensions in the statistical evaluation of the dispersion integral. And in principle, this might be overcome at some point. And then we are again in the situation where the light by light might be at least as important for the uncertainty as HVP.
For the uncertainty.
I should not forget
for the uncertainty.
this.
Absolutely.
For the uncertainty, yeah.
Absolutely. Yeah. You're absolutely right. I agree with everything you said. I'm looking forward to the afternoon where we can fill in more details of this.
Okay.
But this can be done better. But the question is just, when is there motivation again to really focus on this?
Mm-hmm. Yeah, but I think to get this down on the 10% level is actually an important goal, right?
I absolutely agree. I absolutely agree. Sorry for shaking my head and agreeing, but I absolutely agree.
Okay, very good. This seems actually to be a good point to stop discussion for now.